Okay, now for the similitude and model testing and fluid machinery subject. So itong application ng fluid machinery, similitude and model testing, we have the model and the prototype. Prototype, ito yung actual. And model is yung tinetesting mo. So introduction, fluid flow analysis is involved in the design of aircraft, ships, submarines, turbines, pumps, harbors, and tall buildings and structures. Fluid flow is influenced by several factors, and because of this analysis is the analysis is more complex. For many practical situations, exact solutions are not available. The estimates may vary by as much as plus or minus 20%. Because of this, it is not possible to rely solely on design calculation and performance prediction. Experimental validation of the design is thus found necessary. So consider the case of a hydraulic turbine of 50 megawatt. It will be very costly failure if the design performance and the actual performance differ. Diba? If we can predict its performance before manufacturing the unit, it will be very useful. Model testing comes into our aid in this situation. Constructing and testing a small version of the unit is called model testing. Similarity of features enable the prediction of the performance of the full-size unit from the test result of the smaller unit. The application of dimensional analysis is helpful in planning of the experiment as well as prediction of the performance of the larger unit from the test result of the model. Model and prototype. In the engineering point of view, model can be defined as the representation of the physical system that may be used to predict the behavior of the system in the desired aspect. The system whose behavior is to be predicted by the model is called the prototype, yung actual. Okay? Our discussion is about physical model that resembles the prototype but are generally smaller in size. This may also operate with different fluids at different pressure, velocities, etc. As models are generally smaller than the prototype, these are cheaper to build and test. Model testing is also used for evaluating proposed modification to existing system. The effect of changes and the performance of the system can be predicted by model testing before attempting to modifications. Models should be carefully designed for reliable prediction of the prototype performance. So kahit yung mga equipment malalaki, ginagawa ng testing muna. Model testing, plano. Hindi yung sugod ng sugod. Next, conditions for similarity between models and prototype. Models and dimensional analysis provide a good basis for laying down the condition for similarity. So the pi theorem shows the performance of any system prototype can be described by a functional relationship of the form given in equation 1. Pi 1p ng prototype is equal to f of pi 2p, pi 3p, and so on to pi and p. The pi terms include all the parameters influencing the system and are generally ratios of forces, lengths, energy, etc. If a model is to be similar to the prototype and also function similarly as the prototype and also function, then the pi terms for the model should also have the same value as that of the prototype or the same functional relationship as the prototype. So, equation 1. So, ito yung equation 2, pi 1m ng model is equal to f of pi 2m, pi 3m, and so on to pi nm. So, for such condition to be satisfied, the model should be constructed and operated such that simultaneously pi 1m is equal to pi 1p, pi 2m is equal to pi 2p, and so on. So, yung mga pi lang, for example, is the Reynolds number, Prandtl number, Nusselt's number. So, Mayotte number. So, yan, mga yan. So, equation 3 provides the model design condition. It is also called similarity requirements or modeling laws. So, geometric similarity. Mga types ng similarities, meron tayong geometric. Una, Next. Ba naman, okay? So, geometric similarity is yung physical. Some of the pi terms involve the ratio of the length parameter. All the similar linear dimension of the model and prototype should have the same ratio. This is called geometric similarity. The ratio is generally denoted by the scale or scale factor. Parang sa mga plano, 1:100, 1:200, 1:50. So 1/10 scale model means that the similar linear dimension of the model is 1/10 of that of the prototype. Okay, pinapalit niya. For complete similarity, all the linear dimension of the model should bear the same ratio to those of the prototype. There are some situations where it is difficult to obtain such similarity. Roughness is one such case. So in case like ship, harbor, or dam, distorted models only are possible. Distorted model, yung vertical, iba ang scale. Yung horizontal, iba ang scale. Tawag doon, distorted. So in these cases, the depth scale yan is different from the length scale. Interpretation of the result of the test on distorted model should be very carefully done. Makalimutan mo. Geometric scale cannot be chosen without reference to other parameters. For example, the choice of the scale when applied to Reynolds number may dictate a very high velocity which may be difficult to achieve at reasonable cost. Dito na papasok yung ibang similarity. So, papasok na yung dynamic similarity. Ito yung may mga velocity na, di ba? So, similitude requires that pi terms like Reynolds number, Prandtl number, Weber number, etc. be equal for the model and prototype. Yung mga formula niyan, so later na. These numbers are ratios of inertia, viscous gravity, and surface tension. This condition implies that the ratio of the forces on fluid element at corresponding points homologous in the model and prototype should be the same. This requirement is called dynamic similarity. This is a basic requirement in model design. If model and prototype are dynamically similar, then the performance of the prototype can be predicted from the measurement on the model. So in some cases, it may be difficult to hold simultaneous equality of two-dimensional numbers. In such equation, the parameters having a larger influence on the performance may have to be chosen. So this happens, for example, in the case of model testing of ship. Both Reynolds number and Prandtl number should be simultaneously held equal between the model and prototype. So this is not possible as this would require either fluids with a very large difference in their viscosity or the use of very large velocities with the model. So pasok naman tayo sa iba. Kinematic viscosity. When both geometric and dynamic similarities exist, so then velocity ratio and acceleration ratios will be the same throughout the flow field. So fluid, check yung fluid mechanics. This will mean that the streamline patterns will be the same in both cases of model and prototype. This is called kinematic similarity. To achieve complete similarity between model and prototype, all the three similarities, geometric, dynamic, and kinematic, should be maintained. Yan. So types of model studies. Okay, model testing can be broadly classified on the basis of general nature of flow into 4 types. These are 1, flow through closed conduit, mga pipe. 2, flow around immersed bodies, mga ships. Okay, mga buoyancy. 3, flow with free surface. Ito yung mga weirs. Yung pipe din kahit hindi puno. 4, flow through turbo machinery. So, ito na yung mga dito na madiderive yung mga specific speed. Yung mga pumps and turbines. So, unahin natin yung flow through closed conduit. Ito. Flow through pipes, valves, fittings, and measuring devices are dealt under this category. So the conduits are generally circular, but there may be changes along the flow direction. As the wall shear is an important force, Reynolds number is the most important parameter. Mas mga flow. The pressure drop along the flow is more often the required parameter to be evaluated. Compressibility effect is negligible at low Mach number. So M is less than 0.3. For dimensional analysis, the pressure drop can be established as delta P over rho U squared is equal to F of, ibig sabihin, function of rho U L over mu, then E over L, then D over L. Equation 4. The geometric scale is given by the ratio scale is LM over LP. Next note, M model, AP prototype. This requires dm over dp is equal to em over ep is equal to lm over ep is equal to lambda. So yan yung scale factor. So Reynolds number similarity leads to the conditions for velocity ratio. So rho m over lm over mu m is the Reynolds number. Also equal to up over rho p over lp mu p. Then magiging over up is equal to mu m over mu p times rho p rho m times lp over lm. If the fluid used for the model and prototype are the same, then over up is equal to lp over lm. Same fluid, so same properties, ang mu saka density. So is equal to up over lambda. So as lambda is less than 1, the velocity to be used with the model has to be higher compared to the prototype. So otherwise, a different fluid with higher viscosity should be chosen to satisfy the requirement. So the pressure drop in the prototype is calculated as equation 6. So from equality of delta P over rho U squared, equate mo siya. Delta P of P is equal to rho P over rho M times U P over U M squared. Enclose mo siya times delta P M. So this is the drop in the prototype can be predicted. Okay, when Reynolds number are large, the inertia forces are predominant and viscous forces will be small in comparison. So in such cases, the Reynolds number similarity becomes unimportant. However, the model should be tested at various Reynolds number to determine the range at which its effect on pressure drop becomes negligible. After this, it is established. After this is established, the model test results can be applied without regard to Reynolds number similarity in this range. Another condition is the onset of cavitation at some location in the flow, particularly in testing component where at some points the local velocity may become high at pressure may drop to a level where cavitation may set in. Unless cavitation effects are the aim of the study, such conditions should be avoided. In case cavitation effects are to be studied, then similarity of cavitation number should be established. That is PR minus PB over rho U squared over P. So, similarities niyan. Where PR is the reference pressure and PB is the vapor pressure at that temperature. So, ayan. Yung mga example natin later na. Flow around immersed bodies. Aircraft, submarines, car, and trucks, and recently buildings are example for this type of study. In the sports area, golf and tennis balls are example for this type of study. Models are usually tested in wind tunnels. As viscous forces over the surface and inertia forces on fluid elements are involved in this case. Also, Reynolds number of the model and prototype should be equal. So gravity and surface tension forces are not involved in this case, and hence Proud and Weber's need not be considered. So drag coefficient defined by drag force divided by 1/2 of rho U squared L squared is the desired quantity to be predicted. Generally, the following relationship holds in this case. CD is equal to D over 1/2 of rho U squared L squared is the F function of L1, L and E over L, rho U, L over mu. So, ibig sabihin, constant siya, model and prototype. Where L is a characteristic length of the system and L1 represent the other length parameter affecting the flow. And E, epsilon, is the roughness of the surface. Diba, standard symbols naman ang ginagamit natin dito. So, di na ako mag-ano ng cursor. Tumatagal. Yan. So, this may be overcome by using different fluids, say water in place of air, using equation 9, last slide, as kinematic viscosity of air is, last slide, is about 10 times that of water. the velocity will now be at a reasonable level. Another method is to pressurize the air in wind tunnel, thus increasing the density and reducing the required velocity of the model. Where expense of no consideration due to the requirement of utmost reliability as in space application and development of new aircraft, full-scale model are also used. Yung walang problema kung magastos. When same fluid is used for both prototype and model, UM is equal to LP over LM times UP. Question 10. The model velocity should be higher by the geometric scale. If the prototype is to operate at 100 kilometers per hour, and if the scale is 1:100, then the model should operate at 1,000 kilometers per hour, which will mean a high Mach number. So the model will be influenced by compressibility effect due to the operation at high Mach number. The prototype, however, will be operating at low Mach number where compressibility effect is negligible. Hence, the performance prediction will be an error. So, double check nyo lagi kung ano yung applicable. Flow with free surface. Ito naman yung mga sa kanal. Flow in canals, rivers, as well as flow around ships come in under this category. Okay? Hindi ko na igaganon yung mouse. Okay. Sundan nyo na lang yung habang binabasa. In matagal. In these cases, gravity and inertia forces are found to be governing the situation, and hence Froude number becomes the main similarity parameter. In some cases, Weber number as well as Reynolds number may also influence the design of the model. Considering Froude number, the velocity of the model is calculated below as UM over the square root of GLM is equal to UP over the square root of GLP, or UM is equal to UP times the square root of LM over LP is equal to UP is equal to this times the square root of scale. Scale is model over the prototype. Kasi yun ang i-reduce mo, i-enlarge mo is yung prototype. Baka makalimutan. So in case Reynolds number similarity has to be also considered, substituting this value of velocity ratio, the ratio of kinematic viscosity is given as Vm over Vu is equal to scale exponent over 2. So kayo nang bala sa equation number. As this situation involves use of water in both model and prototype, it is impossible to satisfy the condition of equation 12 and 13 simultaneously. In such a case, the distorted model may have to be selected. Okay, so if such surface tension also influences the flow, it is still more difficult to choose a fully similar model. So in many practical application, in this type of situation, the influence of Weber and Reynolds number is rather small. So wala. Hence, generally, models are designed on the basis of Froude number, similarity. So yung mga free surface. A special situation arises in the case of ships. The total drag on the ship as it moves is made up of two components. One, viscous shearing stress along the hull. Two, pressure-induced drag due to the wave motion and influenced by the shape of the hull. Ito yung sa free surface. And as it is not possible to build and operate a model satisfying simultaneously the Reynolds number similarity and Froude number similarity, ingenious methods have to be adapted to calculate the total drag. So the total drag on the model is first measured by the experiment. The shear drag is analytically determined, and the pressure drag on the model is calculated by subtracting this value. So the drag on the prototype is determined using Froude number similarity. The calculated value of viscous drag is then added to obtain the drag. Okay? Saan nyo mabuti. In case of the design of river model, if the same vertical and horizontal scale are used, the depth will be low for the model and surface tension effect should be considered. But the use of distorted model, vertical scaling is smaller than horizontal scaling, so overcomes this problem. Next, models for turbomachinery. So pumps as well as turbines are included in general term turbomachines. Pumps are power-absorbing machines which increase the head of the fluid passing through them. Turbines are power-generating machines which reduce the head of the fluid passing through them para mag-produce ng work. The operating variables of machines are the flow rate Q, the power P, and the speed N. So, mga standard symbols natin yan. The fluid properties are the density and viscosity. So, alam nyo na ang symbols niyan. So, the machine parameters are the diameter and characteristic length and the roughness of the flow surface. So, the power, head, and efficiency can be expressed as function of pi terms as in equation. So, power is F1 times of L over D, A over D, Q over N D cube, rho N D squared over mu. So, the term A over D is nothing important due to the various sharp corners in the machine. So, di na kasama yon. The dimensionless term involving power defined as power coefficient. Defined as Cp is equal to P over rho N cube D cube. The head coefficient is defined as Cs over is equal to Gs over N squared D squared. The term Q over N D cube is called flow coefficient sa mga turbo machines. If two similar machines are operated with the same flow coefficient, the power and head coefficient will also be equal for the machine. So this will then lead to same efficiency. So combining the flow and head coefficient in the case of pump will give dimensionless specific speed of the pump. So NSP is equal to N times the square root of Q over GS exponent 3/4. So this is dimensionless. Ito. So alam nyo na, basta sa consistent ang unit niya, dimensionless. Yung common natin mga later is mawawala yung G, that is dimensional na yon. Okay? Popularly used dimensional, ito specific speed for pump is used defined as NSP is equal to N square root of Q over S exponent 3/4. Dimensional. So, kung anong lalabas ng units dyan, yun na yung dimension niya. In the case of turbine, combining power and flow coefficient, the specific speed is obtained as NST is equal to N square root of P over rho 1/2 and G S exponent 1/4. Popularly used dimensional speed for the turbines is NSTP. NST is equal to N times the square root of P over S exponent 5/4. Yan. Baka makalimutan nyo to. Maalala nyo to, pero ito makalimutan. Okay? In model testing at a particular speed, the flow rate at various delivery rates can be measured. So this can be used to predict the performance of the pump at other speed using the various coefficient defined. The procedure for turbines will also be similar. The model can be run at a constant speed when the head is varied. The power and flow rate can be measured. The performance of the prototype can be predicted from the result of the test on geometrically similar model. So sample problems. 1. Determine the pressure drop in a square pipe of 1 meter side. Square na 1 meter side for airflow. Square pipe, a square pipe of 50 mm side was used with water flowing at 3.6 meters per second. Yung isa naman is water, yung isa air na 1 meter side, yung isa 50 mm side water. The pressure drop over a length of 3 meters was measured as 940 mm water column. Determine the corresponding flow velocity of air in the larger duct and also the pressure drop over 90-meter length. So, yun. Kasi may given yung sa water side na 3.6. Kinematic viscosity of air is 14.58 times 10⁻⁻6 meters squared per second. Density is 1.23 kilogram per cubic meter. Kinematic viscosity of water is 1.18 times 10⁻⁻6 meters squared per second. So given water is W yung side is 0.050 meter. That is 50 mm. Use of W is 3.6 meters per second. Delta PW is 40 mm water column. LW is 3 meters yung water. VW is 1.18 times 10⁻⁶ meters squared per second. So yan mga sa water. Sa air naman, A sub M is 1 meter. L of air is 90 meters. Rho of air is 1.3 kilogram per cubic meter. So density of water, okay lang yun. Andyan na yan. Sa given na yan, pwede na yan ang 1,000. Okay? So, B of air is 14.58 times 10⁻⁻6 meters squared per second. So, ang wala dyan is yung velocity. Flow velocity of air. So, require flow velocity of air and the pressure drop pala. So, solution. For pipe flow, Reynolds number analogy should be used. Also, the drag coefficient will be equal. Yan. For pipe flow. For square section, hydraulic mean diameter is equal to dW or 4A over P or 4AW squared over 4A perimeter is AW, so decide itself. So Reynolds number is UW, BDW over BW is 3.6 times 0.05 over 1.18 times 10 to the negative 6 is 152, then 542. For air, so Reynolds number is U air over D air over B air is U air times 1 over 14.58 times 10 to the negative 6. Equate mo siya sa 152,542. So U of air is 2.224 meter per second. So this is your answer for first required. Drag coefficient is F over rho U squared should be the same for both pipes. So F air over FW is equal to rho air U squared air over rho W UW squared. So the pressure drop equals the shear force over the area. So for section area is A squared, perimeter is 4A. So delta P is 4FL over S. So delta P of air is 4F air, L air over A air. So PW, sa water naman, so delta PW, water yan, 4FW L W over AW. Substituting the dividing and substituting for F air over FW. So delta P air over delta PW is equal to L air over LW times AW over A air times F air over FW. So magiging equal siya ta L air over LW plus A sub W over A sub air times rho, ito na yung ratio. Rho air over rho W times U air over UW squared. Substitute mo na. So delta PR is equal to, bakit ito na lang? This is 7.04143 times 10 negative 4 times 940 is 0.662 millimeter water column. So wait na. Tingnan natin. So ayan. Dito na, delta P over L, delta PW is 90 over 3 times 0.05 over 1 times 1.23 over 1,000. And density of water times 2.224 over 3.6 squared is 7.04140 times 10 is mga negative 4. Dito yan galing. Okay? Then multiply mo na doon sa, ayan, yung ratio times 940 sa water. Ito, di ba? Yung ratio niya. Ayan. Okay? So next example, number 2. In order to predict the flow conditions after the turbine outlet, tail race of a hydroelectric plant delivering 2,400 cubic meter per second, a model of 1 over 75 scale is proposed. Determine the flow rate required. So given QP is equal to 2,400 cubic meter per second, turbine to LM over LP is 1 over 75. Required is QM. Solution, this is a pre-surface flow kasi tail race, yung outlet niya, yung parang lock doon. So, ito, turbine, yan. Hence, broad number similarities to be maintained. So, a model is a broad number of prototype is UM over the square root of LM is UP over the square root of LP or UM over UP is equal to the square root of LM over LP. Okay? Medyo matagal-tagal pag nagmamouse. As flow, Q is equal to AU depends on area which varies as L squared. Pag nagmamouse kasi matagal tapos naghahang pa. So, diretso na lang. QM is equal to 2,400 times 1 over 75 is 2.5 is equal to 0.04927 cubic meter per second. Okay, so paano yun? Q is equal to AU. So, magmamos tayo. So, multiply mo ng, ng AU, EM, EP. So, magiging, QM, QP. Diba? So, yan. So, okay. So, to. As flow Q, yan. So, this is nakakalimutan ulit. QM over QP is equal to AM of UM. Ito yun. Multiply mo lang ng AM. Yan. AP is equal to, since itong area is, ito yon, LM squared over LP squared. Tapos, ito yung ratio ng velocity is square root of LM over LP. So, magiging LM over LP is 2.5. So, magiging substitute values 0.04927 cubic meter per second. This is now your answer. Okay? Lagyan nyo ng answer kasi isa lang ang required. Baka lagyan nyo ng iba, hindi naman answer, so that's wrong. Okay, maglalagay ng answer lang hindi naman required. Number 3, sample. A centrifugal pump with dimensional specific speed SI of 2,300 running at 1170 RPM delivers 70 cubic meter per hour. May SI. SI yung mga units niya. So, also determine the flow head and power if the pump runs at 1750 RPM. Also calculate the speed, the specific speed at this condition. So given d sub 1 is equal to d sub 2 is 0.2. Isa lang ang acentrifugal pump. So isa lang siya. Kaya d1 is equal to d2. N1 is 1170 RPM, NS1 is 2300 RPM, SI, this ang RPM na hindi actual ano. So that is specified na ano, binigay lang ng dimension dyan, pero hindi totoong RPM yan. So Q1 is equal to 70 cubic meter per hour. So N2 is 1750 RPM. Nag-change siya ng speed. So required Q2, S2, P2, and NS2. So solution. So the head develop at and the power at test condition are determined first. So at 1170, the specific speed, doon makukuha yung head. N1, the square root of Q1 over S1 3/4 is equal to 1170. Plus the square root of 70 over S1 exponent 3/4 is 23. So the power, so may nawawala uli. Yung head is 69. Right? So H1 is 6.9 meters. Power P1 is equal to rho G1 S1. Required kasi yung power, wala pa tayong power 1. So P1 is equal to 9810 Newton per cubic meter, 70 times 6.9 times 1 over T6 is 13161. So when operating at 1750 RPM using flow coefficient Q over ND cube as D is the same, so Q2 is equal to Q1 times N2 over N1 is 70 times 1750 over 1170 is 104.7 cubic meter per second. Lagyan nyo lang ng answer. Kasi yan ang required. Di kasi kasya na. So using head coefficient, h over n squared d squared. So d is the same. H2 is equal to h1 times n2 over n1 squared is 6.9 times 1750 over 1170 squared is 15.44 meters. So answer. Okay. So power coefficient, P over rho n cube d5. P2 is equal to P1 n1 over n2 cube. So 1316 times 1750 over 170 cube is 4404. Then specific speed for the model, ns2 is equal to n2 over square root of q2 over h2 exponent 3/4 is 1750 times square root of 104.7 over 15.44 exponent 3/4 is 23. So the specific speed is the same. Ayan. Okay, note that in problem solving, in order lagi yung solution nyo. Determine flow, head, power, if the pump runs. Kasi may purpose yan. Minsan may purpose yan. Ang A, B, C, D, A, B, C. Hindi A, C, A. A, C, B, C, B, A. Hindi yan. Hindi yun formal na pag-solve ng problem. Kahit dito rin, unahan mo yung power, sunod yung head, yun yung flow. Dapat sa given nga, required nga is flow, head, power. Yan. And specific speed. Yan. Okay. So, yan ang normal na pag-solve, hindi yung rumble. Kasi pag rumble na yun, ibig sabihin, kumukopya ka lang. Eh? Hindi mo yun solusyon. So, okay. So, this is the end of this topic. Ito yung prototype, actual. Model is yung maliit. Yan. Remember, pag nag-thesis kayo, pag siya, totoo na siya, at least prototype. Pero pag gagawa kayo ng full demo, maliliit lang sa TISA model.